So this talk is going to be about visual setup and text-based simulations. I know there have been a number of questions about the text-based before. I hope to address those. And the approach that I'd like to take is to start with a visual setup thing that's simple, that we understand, then look at the text-based file that it creates. And then from there, see what we can understand about the text files and how to modify them and use them in the way that you would like to do. I'll tell you a bit about myself very briefly. I'm a senior research scientist here at TechX, been here for more than 10 years now. And my background is in particle simulation, both gyrokinetics and more recently for RF applications, tokamak plasma, antenna modeling and such. I'm very heavily involved with the speed limited particle in cell that John talked about earlier in the day today. And I'm also very involved with antenna modeling for fusion experiments and all the associated kinetic theory. I also do some low temperature plasma simulation, and some of the examples we'll look at today will reflect that. I have a lot of this stuff on my website, which is here. There will be another reference to this later in the talk that I'll point you to within a slide or two, so no great hurry if you don't get it now. And as I said, we want to look at the differences between visual setup in VSim and the text-based interfaces. We've worked really hard at TechX to make the visual setup easy to use and to help you get, hit the ground running with your simulations. So we have a lot of common actions that everybody needs to do in a simulation, grid definition, boundary conditions, and such that we want to make very easy to apply. We want you to be able to look at what you're doing while you do it, and that all works very nicely. As you build your simulation, you have a bunch of different options, electrostatic versus electromagnetic and such, or how you'll do your matrix solves. And in the visual setup, we want to only show you the options that are consistent with that choice that you made. If you pick an electrostatic simulation, you don't want to have to worry about whether to set the electromagnetic CFL condition or anything like that, because that's not relevant to you. So in the visual setup, we hide a lot of the options based on the choices you've already made. That's the right thing to do. And it works for a lot of what users need. And at the same time, it does not always work for every problem. Users tend to be vastly more clever than we are and think of things that they would like to do that we have never envisioned, and yet are possible to do under the hood with the text interface. Sometimes you also want to just go look at your equations and what matrices VSim is building and whether that's the matrix you thought you had and such. All these things are possible in the text base, and we're going to walk through that. That said, if there's a thing you're finding yourself doing in text base over and over again, then it's a good thing to mention it to one of the AEs, and they can very likely work with the visual setup people to make that a new feature. We're always looking for good ideas about what new things to include that people want. Okay, so for this talk, my objective, if you are a new user, you typically have a physics problem, you figure out what it looks like in a discretized sense, you build a visual setup input file and you hand it off to VSim, and some data comes out the back end. It's a bit of a black box in some ways, and we want to kind of pull back the curtain here in this talk. The visual setup file under the hood gets turned into a text input file, and if you know how to create those directly or to edit those directly, then you have more capabilities at your disposal. So we want to understand how this text input file is structured and how the physics and the numerical discretization gets translated into that text input file. What does the interface look like? Understand what edits you can make, what additions you can make and such. Necessarily, this is complicated because Now, the whole point of visual setup is that we want to spare you that complication when you're a new user. But I've tried to structure this talk so that we kind of come gently up the learning curve. We look at things that we are sort of familiar with. We periodically stop and see what we're doing and whether we understand it or not. Okay, this third link on this page you'll probably want to go to right now. I'm going to give you a minute to point your browser there. On this landing page on my work web page here at TechX, I have put all the files that I'm going to be creating in this talk. But what I want to do is to kind of do a live demo of, here's a very simple visual setup file, and then we're going to make it, pre-process it to make the .in file that VSim will use. We're going to look at those .in files, we're going to edit them, and if by chance you fall behind, then I would like you to have those files at your disposal so that you're not just sitting here waiting for me to get to the next thing so you can try and catch up. So if you want to open this third link, you should see a landing page. I'm going to open it now just to make sure that our server is behaving itself. And there it is. You should see something like this. I've got my talk slides up there as well. Another useful link that you can access through the slides PDF or you can access through the txcorp.com website is the online documentation. We'll be referring to that intermittently in this talk. That just tells you what the different parts of VSim do, basically, at the level of detail that you need. And if you want to follow along with the demos that I'll do, you'll want to have your composer open. So I'll give you a second to do that as well. I am not able to see the chat window, so I can't tell if people are asking questions or wanting me to wait or anything. I'm going to ask Colleen if she can.
You are
Let me
okay
know
right
if
now.
there are people wanting me to stop.
Nope, you're okay. You're good for now. I'll let you know.
Okay, next slide. We are going to do a basic electrostatics problem. This is one that you run into in introductory electrodynamics. There's Poisson equation in 1D. So we have del squared phi on the left equals rho on the right. We have a boundary condition on the left and on the right, and this potential is a thing we want to solve for over some domain. And in the ordinary way, we can discretize this equation. We define a grid with some number of cells. We lay down grid points. We use a finite difference approximation for the second derivative, which ties the potential value at one point to its neighbors and to the local charge density. And then at the edge grid points, we have fixed values of the potential or the derivative of the potential, however we want to set that. In this case, I've chosen a Dirichlet condition, so we just assign the potential to be something on the left and on the right. We get a system of linear equations and then we solve it. And you can do error analysis on that and find the normal thing that the error of a spatially discretized simulation like this scales as 1 over n squared. I won't go through that. It's an elementary result. But I want to construct this within VSim and figure out what it looks like from a visual setup standpoint and from a text input file standpoint. So I'm going to open VSim. What I've got here on this screen, everything that's in blue are things that we're going to need to set for this simulation. There's like 17 of them altogether. And I'm just going to try and move this screen so that you can see all of the things that I'm doing while I do them. Okay, so in VSim, we need a new simulation. And here is everything with its default. We're going to need some parameters. I'm going to click on parameters. right click, I'm going to add a user-defined constant called VLeft. And I'm going to set its value to 0, which is already the default. Going to add a new parameter called VRight. Going to set it to 1 volt. Going to add a new parameter called LX, the length in X. That is not wanting to rename itself. There we go. And LX will have length 1 meter. Going to add another parameter called NX for the number of grid cells, which will be 10. And another parameter for the local constant charge density, which I will set to some ridiculously high value of 20 coulombs per cubic meter. All right, that's our parameters. Under basic settings, here we have a drop-down menu, so this is a bit easier. We're going to do a simulation with exactly one step because nothing is changing. We're going to take only one step between dumps because there will only be one dump. It's going to be a one-dimensional simulation. So we'll change the dimensionality to 1. And we're going to pick the field solver to be electrostatic, to do the Poisson equation. All right, that's our basic settings. We are going to define a space-time function for the charge density. Now, I set this constant value over here, rho 0. We're going to put a sine function on top of that so that it satisfies the boundary conditions in a sensible way also. So a space-time function, going to add an expression. And I'm going to call it rho xt. And then it's going to have the mathematical form rho 0 times sine of pi times x over Lx. If I were to right click here, I could access all of the constants and parameters that I've defined previously, and I didn't do that, I just typed it in here, but that's a thing that happens. I have a grid. So I'm just going to set the x min to 0 and the x max to Lx. Let me show you how to access these parameters actually. I'm going to right click here and I'm going to assign the parameter Lx. And for x cells, I'm going to right click again and I'm going to assign the parameter NX. So that's these 3 bits. Then I just need to do my fields and I need to tell VSim how the charge density that I've defined lives on the grid that I've defined. So field dynamics, I need one field. So I'm going to add a background charge density. Going to call it rho. And the expression, I will assign it to this space-time function that we assigned earlier. So that's this rho xt up above. That's that sinusoidal form. So there's my charge density. And I just have left the boundary conditions and the solver. So field boundary conditions, I'm going to right click, add a boundary condition that's Dirichlet. I'm going to call it left PC, and I'm going to give it the value of the parameter VLeft that I said earlier. And this boundary condition lives on the surface lower x, and lower being the left side of the domain, upper being the right side by convention. And same thing with the other side. I'm going to add another Dirichlet condition. Going to call it right BC. I will give it the value of the parameter be right, and I will put it on the upper X surface. So those are boundary conditions within the visual setup context. And then for my solver, I'm just going to do the very basic thing. I'm going to say no preconditioner and going to do the super LU solver, which is just a direct matrix inversion. So there's no interest in parameters here. It's just give me the matrix, I invert it. All right. And that's all. If you fell behind, this file on the download page is called VSim.sdf. And you can just pull it down and we can run with that. So I built a visual setup file with these 5, 10, 18 different changes to the default parameters. And I'm now going to save and set up with this button on the top right. And I will just make a new folder, sim1, save. And what you see is these other files start to pop up here. From the SDF file that I started with that has all the visual setup data, I now have a .pre file with a bunch of intimidating looking macro objects that I'm not going to be dealing with right now. This is basically telling, it's kind of an intermediate step in the translation from this visual setup form to the .in file, the text form, which is the one that we want to be working with and learning how to edit. So this is the .in file. It's basically a wall of text, and it's set off in these nice block structures. I suppose I have a PowerPoint about this, so I'll go back to the PowerPoint for a second. But then we'll come over and look at this text file directly also. So, I already told you that. We have the SDF file, the pre and the in files. And if you look at the .in file, the structure of it is basically a bunch of separate blocks. There's an open tag, the name of the block, and then there's a close tag. It's kind of like HTML if you programmed that. So can go over to the specific file. There's a grid block and it's got some stuff in it. There's a decomp block. No, I'm jumping between windows here. This is not super effective. The decomp block and it's got some stuff in it. There's a multi-field block and it's got other blocks inside it. They each have stuff in them. And so that's the first key concept of a .in file, which is this idea of block structures, that everything you do is going to live in a block for the most part. And in the code documentation, we have tried to document each separate block by the things that it contains and what they're intended to do. So it's a way of organizing the different structures that show up in the code. So we'll have generally an object with its name, with its features, and then a close tag. And we can nest these objects in ways that make sense with the organization of the software. Okay, next concept we want to look at. There's a very big block in this input file called multi-field. And I want to just, without looking at it here, I want to just walk you through the kinds of things that you find there. Multi-field is the structure that holds all of the data that lives on the grids that are in the simulation, whether they're 1 or 2 or 3-dimensional. And within a multi-field, you have both field objects themselves, like electric field or charge density and such. You have mathematical operations that live, or that can be done on the field, gradients or curl or whatever it might be, that live in these field updater blocks. You have various kinds of update steps, both to set the initial conditions for the simulation, those are only done once, and then to update the different fields in a stepwise concept as time evolves through the simulation. Then you have this update step order idea where you combine all of these objects up above, the fields and the operations on the fields and the setting of initial conditions, and then the update into some sequential order that makes sense for the physics you want to do. So multi-field is kind of a big part of what goes on under the hood insofar as fields are concerned. There's equivalent size blocks for particles, which we'll talk about a little bit later. But all of the electrostatic, electromagnetic kinds of operations that you're used to, electric field and charge density and such, are going to be tied to this multi-field block. All right, now we get into kind of the guts of this. And I should point out before I start talking about this that the documentation side, if you go to txcorp.com, there will be a tab for documentation that hopefully is pretty easy to find. Actually, I'll just go find it now and show you. So txcorp.com, and if you go to product, documentation, that will take you to the VSim documentation set and also all of our other product documentation. But for this talk, VSim is it. So here we have all of the different features of our software explained, hopefully in a way that's accessible and easy to work with. So I have this block here like a grid, and if I type in the search bar grid, then I can find descriptors of it, and then I can find the description of the object. I'll click through here, and so here is a description of the grid block, all of the parameters that you'll find in a grid block, all of the different kinds of grid blocks that you can make, and the parameters tied to the different kinds and such. Jumping back to the PowerPoint here, every one of these separate blocks is going to have a documentation entry associated with it that you can go look up. And I'm not going to tell you about everything in every block because that would make this talk very long and dull. But whatever you need to know about a block, you can find in the documentation by looking at the class, the object itself, and then look for that in the documentation. Okay, so in this input file we're looking at, I've just copied and pasted bits of this. Again, we've gone from the SDF file over here to the in file, the text version of this Poisson solve in 1D that we built. And I've just cut out bits of this file that you see on the right, put them into my PowerPoint on the left. We can talk about what's there. A bunch of things that make a lot of intuitive sense. The number of time steps in your simulation, how often you want to create dump files versus the number of time steps. If I want to run for 10 steps, but only have one dump file for every 10 steps, I can change this periodicity setting. I can set my time step. I can set the dimensionality of my simulation and whether I'm using a verbose kind of output from VSim or whether I want it to be sparse. All these very basic particle simulation things. Dropping down to the grid, I have these similar kinds of accessible grid parameters. How many cells are in the grid? How big is the grid? Where does the grid start in a Cartesian space and such? So none of that is terribly surprising, and if you want to learn more about what these other parameters are, you can read the documentation. We have various fields. We have scalar fields with one component. We have vector fields with 3 components. We can have tensor fields also, but I'm not going to talk about that. And these fields live on the grid in various configurations. Some of them are edge fields, like this electric field vector. It lives not on the grid points, which are these black dots, but on the grid edges, which are these lines between the black dots. If you think back to how E is the minus gradient of phi, that gives you a nice centering. Phi lives on the nodes, and if you take the center difference derivative between these 2 points, then you get a quantity that's centered on the edge between them. That's the electric field. And then there are various rules about how these fields should be messaged with the overlap parameter and with the kind of field. And then we have these dependent fields that collect data from particles. Then we have these regular class fields, which are pretty much exactly what they sound like. And we can assign labels to the fields, and so that in our output file, it's easier to figure out what they are. Yeah, kind of dwelling a lot on this, and I'm going to skip ahead a bit because what you really probably want me to get to is the looking at the .in file and editing it and such. So just say that we have field updater blocks that define mathematical operations on fields. Here's E is minus grad phi. And we have other field updater blocks that bring in parameters that we set. We have this charge density updater, which, if you'll recall, we set an initial charge density times a sign function, and that shows up in this expression in the field updater that this is the charge density that you picked. And we have various update steps. We have ones that happen at the beginning where we take the charge density and set it, and then we do an initial solve to find the potential associated with that initial charge density. And then we take the gradient of that potential to get the initial electric field. And then we have the regular update steps, which if we were doing a more complicated simulation with particle motion and changing charge density and such, then these would be more important. But for now, they just look the same as the initial conditions. We take the charge density, we compute the potential from Poisson's equation, then we take the gradient of the potential to get the new electric field. And that's set up in this step order here. All right. So going back to what we were trying to do to begin with, we built an SDF file. We used the visual setup. And then we looked at this complicated text input file, the .in file, that VSim created from our visual setup work. We saw that this .in file is set up in various blocks. We saw that you can go and read the documentation online to look at what the various blocks mean and what they do. And we looked at some of the kinds of blocks that you will see as you do that. So that is kind of introductory text files. And we created a thing, and here's what showed up. Okay, now we're going to do matrix solves, and I talked about this a little bit. A lot of what you will do in electrostatics is to construct various matrices to solve for the electrostatic potential, and ideally that's done under the hood. Sometimes when we do that, we are not super confident that what we think we're solving is the thing that actually is getting solved in VSim, and we want to go and verify that. It's less easy now to make errors in that process than it used to be, especially with the visual setup. But occasionally there are weird glitches that pop up, and you want to check and make sure that this all makes sense and hangs together. So I'm going to go back to this physics problem we proposed, and we're going to do it by hand in some elementary sense. Yeah, I told you how we discretize it and how we have this center difference approximation and then boundary conditions and such. And what that looks like in practice is a matrix vector multiply. So here is the equation for the Poisson equation in the areas of the domain away from the edge. So we have a second derivative of the potential, which lives in this approximation. We have a charge density on the right-hand side. So what we do is we line up all the potential values in a vector, which is here. We line up all the charge density values in another vector here, and then we build the matrix that operates on the potential to get the charge. What we'll ultimately do is to invert this matrix on the left. We have an AX equals B form, and we want to invert the A matrix in order to find what this potential vector is. That looks like this in the manual construction, if you will. We have the 1 minus 2, 1 structure. It's a block tridiagonal matrix, and coefficients out front and such. And then on the first and last rows, things are special. We can't reach back over into the -1 grid cell. So we have to just set our boundary conditions there. So we do that by just setting the corner elements of the matrix here. We say that some coefficient that undoes this coefficient out front times the phi 0 is the phi 0 that we want. And I put these rescaling factors in, gamma and mu, because when you're inverting a matrix, and more so if you're doing it iteratively, the condition number of the matrix can become problematic. And if you look here, you have elements of order 1, minus 2, 1 going down the diagonals here, and then elements of order delta x squared, which is tiny, times 1 over epsilon naught, which is enormous. And it may be that these corner elements are vastly bigger or vastly smaller than these diagonal elements of the matrix otherwise, and that messes with the condition number. So you can rescale these elements so that all of the matrix elements are of comparable size. That has better numerical properties for your matrix inversion algorithms. Now that we built that matrix, it's in our normal AX equals B form where we want to just invert A. And so what we'll do is to look at how that's done in the input file. We have a linearSolveUpdater block in the big complicated .in file that we looked at earlier, and that is basically geared towards solving these kinds of equations. AX equals B. I give you a matrix, I give you a vector, and you tell me the inverse matrix times the vector to find that unknown X. So, in the comment about boundary conditions that was made earlier is going to become important here very shortly. This field updater, the linearSolveUpdater, has a bunch of parameters associated with our domain. It has lower bounds. These are basically describing the grid that we are solving the equation on. It's like Python in that if you go from 0 to lower bound 0, upper bound 11, then you are only counting from 0 to 10 in the number of points that you're including. So inclusive lower bound, exclusive upper bound. We're going to read a field, the scalar component of it, because it's just a scalar, and then we're going to write the field, the phi field that we get from inverting the matrix and multiplying it by the charge density. We can look all these up in the documentation and such. We have this right equation to file parameter that we are going to edit and change and look at what comes out. That lets us basically view the matrix that we're building in VSim. And then we have also these matrix filler blocks, which I'm already running a little bit short on time, it looks like. So probably not going to talk about these extensively, but you'll have the slides accessible if you want to dig deeper into it. basically we have matrix filler blocks, which are going to define these different matrix elements. I think I've talked about this more on the next slide. Okay, yeah. We get a whole list of stencil elements, and these look a little bit intimidating and awful, but if you go and read the documentation, sort out what they mean, it's not too terrible. We have a value for the stencil element. This one is going to be 1 over delta x squared. And then we have an offset saying, are we 1 to the left for the center difference approximation, or are we 1 to the right, or are we the central element in the center difference approximation? So basically your Poisson equation, if you look down here at this coefficient array, and we have a coefficient out front, the epsilon naught over delta x squared factor, and then we have a -1 element, and then we have 2 central elements, and we have a +1 element. These two are separated out because if you're doing a more complicated Poisson stencil on edge fields or something, then you need to distinguish between the one on the left and the one on the right, but that's not super relevant here. In any case, we can use these stencil elements to look at how this row of the matrix is built. And this is the away from the boundary. Then we also can apply boundary conditions. We have a different matrix filler and a vector writer block for the top. This is the top row, I believe. No, sorry, this is the bottom row. So it goes from 10 to 11. Now only the first dimension is relevant here because this is a 1D problem. So this goes from grid cell 10 inclusive to grid cell 11 exclusive. So it's just the 10th cell. And in that 10th cell, we're going to give the stencil a value of this 2 epsilon naught over delta x squared factor that showed up on the top row earlier. That's this scale factor. And then in the vector writer, this is basically to build the corresponding right-hand side. We have a boundary condition filler for the matrix. We have a boundary condition writer for the right-hand side. Again, that only lives in the rightmost cell. And it has value 1, which was our boundary condition that we applied in the input file. This, if you recall back to this parameter that I set, I had 0 volts on the left, 1 volt on the right. And then the scaling factor is the mu factor, so that our matrix condition number is tidier than it would otherwise be if this were a 10 to the -9 factor in the corner of the matrix and everything else was of order 1. That would not be as easily dealt with. So that is essentially what boundary conditions look like for planar surfaces. That I have some specific matrix filler element to build the matrix. I have a vector writer element to build the right-hand side, and they're going to only live in these narrowly defined regions of where does the boundary of the simulation sit. And then finally, we want to tell it that we need to solve an AX equals B equation. We need to tell it how to do that in this direct solver kind in the linear solver block is what does that. There's lots of options for the different kinds of linear solvers that you might want to use in VSim, and all of the other ones are more complicated than this 3-line thing, but they're all accessible in the documentation. You can look up the different optimization parameters and figure out what is best for your particular problem. All right, so now we are going to do some editing, which everyone's been sitting here thinking, finally, when is he going to get to that? There's a prominent warning up here above this .in file that I should not, in fact, edit this file. And the reason is this: if I go back to my visual setup and I change something. I'm going to maybe change this parameter for the right-hand voltage to 2 volts. Then it says simulation has changed. I need to save and set up. And so I click simulation, click save and set up, and it builds me a new pre-file and a new in file. And the old in file that I had before with 1 volt is completely gone now. It's gotten overwritten. What that means in practice is if I go in here and I try to change things, which it does not look like I can do actually, likely by design, it doesn't matter because when I hit save and set up, all those changes will get overwritten and go away. So what you need to do if you want to make a change is to go and actually copy this .in file that you're working with to somewhere else. I'm going to go and do that in my terminal. I have sim1, that's where we sit, and I have a vsim.in file right there. I'm going to make a directory sim2 that sits at the same level as this one that I'm in. I'm going to copy vsim.in to the sim2 directory, and I'm going to call it vsim.pre. Okay, why did I call it .pre instead of .in? The reason is because when you open up Composer, it looks for files, first SDF files, and then for pre-files if it doesn't find any of those, and then in files if it doesn't find any of those. I'll show you what that looks like now. So I'm going to go open, and I'm going to go up. And here's sim2 that I just looked at. If I go into sim1, it'll find this SDF file that'll pop up a nice visual representation on my screen of the thing that we built earlier. If I go into sim2, there's no .sdf file, so we don't want to be working with those right now. So it opens up the pre-file, and it's, oh, I can't actually show you anything. All that I can show you is the input file. And I'm actually wondering in here if I can edit this or not. I'm going to find that out. Everybody who already knows the answer is going to sit here and laugh at me. But, okay, what we're going to do in here, I'm going to, in the pre-file, I'm going to change this parameter. Right equation to file now equals 1. And this is editable, it looks like, so that's good. And now if I click validate, that will save my changes. And then I can go over into the .in file, the text input file that we're learning to edit. And I can go and see that that parameter is still 1. So pre and .in files are kind of interchangeable in this sense. If you have built the pre-file from an in file that you've already created, there's technical details of why you would call it one and the other, and not super important right now. But basically, we can edit this .pre-file within Composer. We can validate the simulation, and it will tell us if we've made any serious errors or not in the edits that we made. And if we haven't, we'll get a good .in file out that we can then run with. I'm going to do that now. It's going to run for one step because this was a very dull single-step Poisson equation. And what you'll see if you then go into the file browser is that in addition to the output that I could look at here, there's a charge density and electric field and all this stuff. There's also these .mtx files, which have all the matrix data that I wanted. You know, I changed that parameter right equation to file to be true and 1 instead of 0, true instead of false. And because I did that, I get these new files that I can then go in and look at. I wonder what happens if I just double click. No, can't open it. So I'll go into my terminal and open instead. Oops, I'm still in Sim 1. Okay, so I can open the solve matrix.mtx file, and this is just a 3 by n list of the matrix element 1, 1. Okay, I have a list, a matrix that's 11 by 11 with 29 non-zero entries. The matrix element 1, 1 has 0 that, or has value that. The 2, 1 element has value this, so on and so forth. You can, if you know what you're looking for, you can back out what those mean. So here is my listing, and you know that your matrix ought to look like minus epsilon naught over delta x squared times these factors going down the diagonal, the minus 2 and the 1. You can check that numerically to verify that indeed these long ugly numbers are actually the factors that I wanted to be in the matrix. And you can check your boundary conditions this way too. If you had put a Neumann condition on instead, then your top row of the matrix would look slightly different here. And you can check to be sure that your scaling factors were correct and that you had everything set up in the way that you thought you had. Then you can do the same kind of thing for the x and the b vectors, the charge density here that you've defined. You recall that I defined the charge density like this in our visual setup input file. And then the potential that you solve for, which has these kind of ridiculously high values because I chose such a large value for the charge density. But basically, if you get the A matrix right and the B vector right, then this linear solve updater that does the direct matrix inversion will give you the potential that's consistent with those values. All right. So we've only done actually one edit, and this talk was about editing the .in file and giving you 50 minutes of introduction to that concept. The reason that I've done that is not because I don't want to show you how these things are edited, but more I want to show you the philosophy of what is in the .in file that I can look at, that I can edit, and more of the things that you'll want to do as you edit these are based on kind of building a simulation that you already understand in the visual setup, and then changing it slightly so that you're not having to build this whole 350 line input file and all the stencil elements and everything by hand. You want to do as much as you possibly can in the visual setup, and then only change the text file in the ways that you need to, because that will help you to make fewer mistakes in syntax and in all the details of these little block structures that I've shown. That said, most of the interesting problems you'll want to do are not one-dimensional, and they are going to involve particles and complicated geometry and such. I'm going to cut a little bit ahead in my talk. It's not too terrible to generalize our 1D simulation to a 2D simulation. What you would see if you did that is that we need to apply more boundary conditions and such. And we need some more parameters to describe the other dimension. We can generalize the charge density to be dependent on x and y both and such. What you will see if you then print out the matrix is that it's much larger. It's got 2D structure, and so we have this off-diagonal block structure coming down, a band structure, I guess I should call it, because now the charge density matrix lists all of the all of the first row of charge density and all of the second row and all the third row as we march across the grid. So as you're reaching across to do the Poisson solve in 2D, you have a diagonal element here, and then you reach to your neighbors to get the x differences, and then you reach kind of a step over to get the y differences. And if we were to generalize this still further to 3D, then we would have another band structure. The matrix would be enormously bigger, but still sparse. We'd have more stencil elements and such, and I'll jump over that. You can look at that on the slides after this presentation in more detail if you want. And I think in the interest of time, what I will do now is just give you a broad overview, and all these input files are downloadable from the site that I pointed you to earlier. So what I had planned to do originally was to just add some basic things to a simulation. We're going to add a perfect cylindrical conductor that sits in the middle of this 2D thing. Then we will specify what it's made of and where it sits and how it's oriented and such. And after we did that, we get this SDF file in the visual setup. It'll look like this, and you can download it, as I said. You can then do the save and setup button, and you can see that new block structures will pop up in our .in file that are associated with these changes that we've made. We'll have a new material with certain physical parameters associated with it. We will have a new grid boundary object, which will be this cylindrical shape that we dropped into the middle. That will not have a nice, simple representation in the matrix elements because it's got all these cut edges and such. So there are different parameters that we need to think about in terms of how the edges of that shape cut across our grid and how we handle the small faces and edges that result from that. These are all described in the documentation. And as needed, we can edit these parameters to get results more in keeping with what we think we should see. This is just a quick look at what the cylindrical object looks like in the matrix representation. We have a grid boundary object, and it lives on the entire grid. You remember that I went from 1 to 10, and then if we had done the 2D, I had gone from 1 to 15 there. There are various operations with cut edges and cut cells that go on that are described by these interiorosity parameters that tell you how the shape interacts with the grid. And then there are various stencil elements, as before, that tell you what the potential value is on this cylindrical object, and so on and so forth. It's just a slight generalization of the thing you saw earlier, where we were doing it on this regular rectangular grid. And then if I were to go into VSim from a particle point of view, there would be more things like this. I'm gonna do this part because particles is a big part of what goes on here. Where's my composer window? All right. And I'll just open this thing up that I did before starting this meeting. This is one of our examples. This is a capacitively coupled plasma in one dimension, and it has particles, and the particles essentially slosh back and forth between two capacitive plates. If you go to the .in file here, what you will see, there's some stuff that's familiar, number of steps and the time step and such. And multi-field block is still there, of course. And there's a couple of new structures. These are the particles that we model, and I'm not going to say a lot about this except that it's the same kind of concept. We have nested block structures. It's just like the multi-field in that there's a top level block that's the particle species. There's some descriptors for it. What is its charge and mass and such. And then there are these sub-blocks within it that tell different aspects of the species and its behavior. There's particle source blocks, which do exactly what they sound like. This is how you put particles in. There are position generator blocks to tell you where the particles should start, velocity generators to tell you what their initial coordinates should be in the velocity space. There are particle sinks. And now none of these things are particularly complicated. They just kind of all bundled together in this species block. That's the top level block. And so multi-field is for fields, species is for particles, and then you can go and look at the different subblocks within there to get a sense for and what are the different moving parts in this thing and how do they work and what do they do. I talk about a few of them here, which you can look at the slides later and figure out. But I think I will just cut a little bit to the end here in terms of what I hoped to do here. The main thing I hoped to do here was to show you, now we have SDF files, we have the nice visual setup, and you can get very far with that. When you're to the point where you can't get any further with that, you're going to have these big in files with all the different block structures and such. And it looks a little bit daunting at first. What I hope is coming out of this is that all of these structures in the .in file, you can look at kind of in terms of little subunits. Each block has its own separate identity and capabilities, and each block is described in our documentation. I don't envision that anybody will want to actually sit down and write an entire .in file by hand without referring to anything else. But what I envision the workflow as is that you'll build something that's kind of like what you want. You get as much done in visual setup as you can, then you'll get a .in file. Then you can do the operation I showed where we take that .in file, save it in another directory as an editable pre-file. And then we start adding the things we want. We have VSim do the checking on it and validation to make sure we did that right. And then you get very much closer to what you want, hopefully in as painless a way as possible. You should certainly ask questions if you get stuck in that process. Our application engineers are able to help you resolve things that come up through the process. You're likely not the first person to have dealt with any particular problem, especially if you're getting started with this idea. But Perfect. At any rate, that is how things look under the hood, and I hope that that's been helpful to you. I will take questions now. I see that something is popping up in the Q&A. There we go. Okay, 2 questions from Salvador. At what point do you decide that a problem needs to be set up in the text editor versus the visual interface? I would say do as much as you possibly can in the visual interface, but I'm not sure I can speak more generally or more specifically than that. Certainly we have capabilities to set up a lot of things in the visual setup, and John demonstrated some of those, and Trey also. Certainly if you're using an experimental code feature like the speed limited pick that John was talking about earlier, that is not yet in the visual setup, and you'll need to be using the text interface there. Okay, question, how to decide lower bounds in a boundary condition, when to choose 0, when to choose -1. In some sense, that depends on the type of problem you're doing. It's often the case that if you have particles, you want to make your absorbing region and your boundary condition slightly thicker in the event that you get a particle that happens to be too fast and can pass through more than one cell inadvertently. Also, it may apply when you are doing edge-centered fields versus node-centered fields. But typically, the visual setup will get you oriented correctly as far as how the boundary conditions should be applied, at least in a basic Cartesian geometry. And I have not used the others enough to comment on those, but I can't imagine that we're doing a worse job there. So, what kind of shapes can we import? Our geometries, it says only limited to default CSG shapes. I'm interested in an elliptical torus, and remember that a couple of versions ago there was a way to generate more general shapes in terms of Heaviside functions.
Oh, yeah, for sure. There were a lot more, and we just didn't make them available in the visual. And so, you can look at some of the other ways of doing it. There's pretty much, you can do anything you want with the Heaviside functions.
Okay, but that is not in the visual setup, then that's the clarification.
That is not in the visual, nope.
Okay, so
but a user could also, if they were, inclined, make their own geometry in a CAD program and then just import it also.
And is that possible to, let's see, no, I guess that wouldn't be possible to do in our mesh, and you'd have to import that externally.
Yeah, some other CAD program.
Okay, so Salvador, I think that's responsive to what you were hoping for. We would need to go to the text interface at that point and use the Heaviside functions and such. I should mention that the slides that or the website I pointed you to earlier also has these slides on it that I've just shown you, and I've skipped over quite a bit in the interests of not running too far over time, but if you want to dig in more detail, you can certainly download the PDF from there. There is a question about how one might make a parameter sweep using text-based setup. Okay, actually I can take this. Basically, for a parameter sweep with text setup, you will want to identify as best you can the parameter you're sweeping over, and you're going to just make a bunch of copies of your .in file and put in that parameter. And that might be a bit complicated insofar as if your parameter is like a grid resolution or something, that will propagate all the way down through your file. One of the differences between a .pre and a .in file is that we can put various parameters in that context. And John Carey is saying that he would like to address this question. And so I'm going to kick it over to him. John, are you able to talk?
Thanks.
Okay.
I assume I can be heard.
I hear you.
Great. So what you need to learn about, the .pre file allows you to take any parameter and define it in the pre file with a $sign syntax. And then you pre-process it using this thing called TXPP. This is really an advanced topic. But TXPP is what we call our preprocessor. And it can create the thing with the variables, the .pre file, and turn it into a .in. And there is a syntax that looks something like this. I'm going to put it into the chat window. I think I'm going to put it in there. No, I seem to have done exactly the opposite of what I wanted to do. So it doesn't look like I can send it to all panelists and all attendees.
Panelists are just, all attendees.
So I don't, there we go. So I can do something like txpp.py and this txpp, and I'm going to write this out, and then we can talk about it. And you have an input file and an output file syntax, and I've forgotten what it is exactly, but you can say something, and I'm going to send this in just a minute, if I say my param equals 0.3 and, you know, foo.pre like this, then what it will do is it will translate foo.pre, and no matter what you have set your my param into inside of foo.pre, it will change it to being 0.3. So now you could do lots of things. You can write a code in Bash, or you could write a code in Python, whatever, and that code then just has a simple loop, and it calls this TXPP. Then you launch Vorpal with the resulting .in file as its input file, and then Vorpal will run with that new parameter. And then when the Vorpal is done running, it goes to the next point in the loop, and then you change my param to something else in your loop. This is really an advanced topic, and I realize that what I'm telling you is, I don't know, it's kind of like air math, you know, it's the nerd's equivalent of air guitar. You know, I can't really show you all the equations here and all the code calls, but there is a way of doing it, and it uses our preprocessor to just substitute a value, and then you do another run. So
And the
maybe
output
that's
of
a
that-
good thing for an advanced topic. Pardon?
The output of that is a .in file.
Yeah. So this gives something, this gives, hey, I'm going to write this out, a foo.in with evaluated with my param dot equals 3. And so then write a loop in the language of your choice. Python, some people like Python, some people like Bash. And in the loop, you loop over your scan of my param.